So Preparedness Week is just around the corner, and really severe weather is just around the corner. I mean, that's what this is all about. This program is to help refresh the memory of those who've been through this year in, year out. Just a show of hands, who's first-timers here tonight? Any of you? Actually, a fair share of you, so that's oftentimes the case. And so with that, we cover the entire gamut. Our focus on today's presentation is a couple different things. One is the interpretation of radar data. There are certain signatures that are typically tied to severe weather. We also find there are certain signatures in the cloud patterns that are tied to severe weather. And those are going to be our focus here tonight. So when you leave here, you'll have hopefully a better comprehension of what to be watching for on radar, what to be watching for in the sky. And hopefully what you'll see too is those two pieces of information work together in concert with each other. So as mentioned many a time, storm spotters and their importance and why you play that role. Well, we all know that Indiana experiences severe weather. We haven't had any so far this year to speak of, but we know that's just around the corner. The Weather Service mission is to protect life and property, and we do that through the issuances of our watches and warnings. That combination of you, the storm spotter, which are our local eyes and ears on what's taking place here, and the technology that we use back at the Weather Service, their hope is that combination will help save lives. As was also referenced here, we do that for a reason. The radar has limitations. That radar, which is located by the Indianapolis airport, that radar beam is gaining altitude with distance, and as Dale had made mention, 1,600 foot above ground in the southwest corner of this county, up to 4,500 feet or so on the northeast corner. So the beam is well above the ground, and a lot of things happen at the lower ends of the cloud base and below cloud base that we cannot see. In fact, much of what we are looking at on radar, we're inferring what's going to be taking place on the ground based on what we see taking place on radar. But again, that's those reports that make the difference. So a few definitions to begin with. First off, we're going to start with the Storm Prediction Center. That's the national arm of the Weather Service that their sole function is to keep an eye on that potential for severe weather. And they provide graphics on a daily basis. And the graphic you see on the upper left is an example of one of those types. So areas that you see shaded in light green represent locations within the country on that given day. This is their day one outlook that may have thunder take place. Moving inward into the darker shades of green are a representation of areas where there's a slightly elevated risk for the potential for severe weather. And as you work your way continuing inward into the yellows, that's into a slightly higher risk, the orange even higher still. And in this case here, the area shaded in red is what is referred to as a moderate risk for severe weather. And that's a fairly high risk. Moderate is the second step up from the highest that the Storm Prediction Center places out there. Their highest is the high risk. Generally, when we see moderate or high risks in effect, those are usually followed somewhere later on in the day, depending on the timing of the storms, with tornado watches. The blue dots represent wind reports, green dots represent hail reports, and red dots represent tornado reports. And so there were a lot of wind reports on that particular day. When it looks like active weather is going to come to a point where we may have severe weather break out, the Storm Prediction Center gets in contact with local weather offices, and we talk on the phone and make decisions with regard to where counties should be or should not be involved in the areas outlined in these polygons. So here's an example in which we have a couple of severe thunderstorm watches in effect in the same time. And severe thunderstorm watches mean that there's that potential for severe weather to take place. And again, those are issued by our local weather offices. When we reach a point where it looks like severe weather will in fact occur, that's where we issue warnings. So in this case here, this area outlined with the red outline here represents the area that is going to be warned for. And so in that scenario, there's an expectation that we'll see winds near or above 60 miles an hour, hail 1 inch diameter or larger, or perhaps it may have been a tornado warning with the expectation of hail. Now, a little bit on radar basics. Image on the left-hand side, you're familiar with that. It's referred to as the reflectivity data. It's the measure of the amount of the precipitation's intensity based on the amount of rain droplets and or the size of the droplets and or hailstones that are within the thunderstorm or atmospheric column. The color scheme is such where you're looking at blues and light greens. We're looking at light precipitation. As you work your way into the yellows, you have a little bit heavier precipitation. By the time you get into the red echoes, you have very heavy precipitation. precipitation, and in many cases, in most cases, you'll also have lightning associated with those red echo areas. And then finally, within inside that, these shades of pink and purple represent areas where hail is also occurring within those thunderstorms. And it might be pea-size hail in such great quantities that it might pile up to 2 inches deep on the ground, or it might be a handful of softball-sized hailstones. And we really don't know the difference by looking at that radar, which of those two outcomes is going to be the likely event. This is where you, the storm spotter, come into play. Green's a measure of motion towards the radar. Red's a measure of motion away from the radar. The color scheme is also designed such that the darker shades of green and red represent the weaker wind speeds, and the brighter shades of green and red represents the stronger wind speeds. So right between these two yellow arrows in both these locations here, we're looking at what we refer to as a rotation couplet that is tied within the hook echo portion of the storm. That's the center of rotation for those thunderstorms that's also producing the tornado. So again, in both cases here, this rotation couplet right here ties in with this hook echo here, and this rotation center right down here, bright green inbound, bright red outbound, is tying in with this rotation feature here, which is also producing a tornado at that moment in time. A little bit further on the radar data, the left-hand side, the Joplin, Missouri EF5 tornado. And again, you can see the same concepts being applied here. In this scenario on the left-hand side, the radar is located to the right here. So again, green inbound towards the radar, red outbound away from the radar. In fact, we're using the warm and cool color wheels. So in the sense or the case of the green inbounds, you see that you work from a darker shade of green into a lighter shade of green into light blues, dark blues, and eventually to purple. Again, increasingly strong inbound wind tied into that cool side of the color wheel. And on the opposite side of the coin, dark red to light red to pink to orange, indicating increasingly strong outbound wind. But again, that very strong inbound, outbound adjacent to each other represents the rotation couplet, the mesocyclone or small scale rotation that this thunderstorm in fact is, and right at the heart of that being what we call the tornado vortex signature, the bright orange outbound right adjacent to the purple inbound, indicated by the white arrows there. Now, with regard to thunderstorms, they go through a life cycle, about a half hour from beginning to end in your average everyday summertime thunder shower, from on the left-hand side where you have your initial warm updraft forming that storm, to a point where as it continues, where you have a very strong updraft that's feeding that storm, creating precipitation that's cooling the atmosphere, falling down towards the ground, the wind spreading outward. That's at our mature stage. And you see associated examples of clouds that are matching with those here, to the eventual dissipation stage, where in this case here, your updraft is essentially cut off or minimized, no longer feeding that storm, and it becomes downdraft dominant, and then the storm begins to dissipate. So again, about a half hour in life cycle on that. Now, it takes a lot to form storms. The ingredients that we look for, obviously a source of moisture. In fact, what we're looking for is not only moisture, but contrast is in the atmosphere. The more heat and humidity that you can pump in at low levels in contrast with cooler and drier air that you bring in from aloft creates a very unstable atmosphere. So an unstable condition is one thing that we look for. Another thing that we look for is some way of mechanically lifting that unstable air. Our frontal boundaries serve in that capacity. So a warm front pushing north out of Kentucky or a cold front heading east out of Illinois, those mechanical boundaries force the air out ahead of it to rise up over those boundaries. As you rise that unstable air, it begins to form that thunderstorm, and with sufficient lift, instability, and one other component, these storms can become severe. That other key component is what is referred to as wind shear. By wind shear, what we're referring to is this. As you take a look at the diagram on the left-hand side, you see this thunder shower updraft. The yellow arrow indicates the updraft. The rainfall you can see is falling there. The black arrows on the left side are a representation of the atmosphere's wind profile from ground level to high altitudes of the storm. Each one of those arrows' length is a measure of the strength of the wind, and you can see they're all of equal length, meaning that there's no change in wind speed with height or no shear in the atmosphere. In such a scenario, as the updraft forms by the unstable conditions, it generates precipitation, which then falls back down into the updraft and essentially kills it off, and that's the end of that particular feature. Now, when you introduce increasingly strong wind with height, which is referred to as the speed shear, and that's indicated by the increasingly long arrows with height here, now you have a scenario by which that updraft that is being formed is interacting with that strong wind aloft, and that strong wind aloft will physically tilt that updraft forward with height. What that then does is that allows this precipitation to fall out separate from where the updraft or the energy source is. And by keeping that energy source alive, that allows this storm to become long-lived. These things can be measured as you go to their meso analysis page. They have lots of data. This is just a sampling of a couple of those, but they represent the ones I've just talked about. So we've talked about instability. CAPE is a measure of the atmosphere's instability, and it stands for Convective Available Potential Energy, along a bunch of words, which simply means the energy that's available for convection. So the more heat and humidity you pump in the lower levels in contrast to cooler and drier air aloft, that creates an unstable condition. On these charts here, anywhere where you have contouring available or displayed, that's an indication of CAPE values that are at least on the order of 500, and those are usually sufficient for some amount of convection to form, and usually when your values above 1,000, you're looking at pretty significant values. And as we look over here to the right-hand side, that represents the shear, or the increasingly strong wind with height, or the difference in wind speeds between higher altitudes and lower altitudes, which again allows for that updraft to tilt forward with height. Again, anywhere where it's contoured is a representation of where the shear is sufficient, and as you work your way inward with the contours, say for example here across Illinois and into Michigan, the values are quite high. A very strongly sheared atmosphere is one that is often conducive for significant squall line development that also produces tornadoes within those squall lines. Down on the bottom is what we call the supercell composite. It actually is a combination of those two features together, combines both the effects of instability and shear in the development of a storm that can have rotation and thus become a supercell. And again, anywhere where the data is contoured represents areas where supercells may form, but in general what we tend to find is that the most active supercell development tends to be where those values are highest. And in this given case here, those values were quite high over central Illinois. So again, these are products that are available from the Storm Prediction Center from their meso-analysis page. They're updated each and every hour, and you watch those for the changes in the environment over the course of that hour's time frame to see if the atmosphere is getting more unstable, stronger shear, meaning stronger storms, or if it's going in the reverse sense and reducing that potential for severe weather. In this slide here, we're also throwing in the additional component with regard to shear, that being directional wind change with height. So here in this example, we're looking at a surface wind out of the southeast at a speed around 20. As we work our way to cloud base, we're out of the south with a wind at about 50. We work our way through the depths of the cloud, and you can see the wind speeds are increasing and changing direction with height. So not only do we have the speed shear present, but now we also have that rotational component, which is simply one additional factor that increases the likelihood that that storm will rotate. And so in this time lapse here, you see exactly that happening. You see the rapid upward growth of this storm, in part because of the instability present, but you can also see a little bit of this kind of sideways twisting that's occurring, tied with the increased shear with height as well as the directional change of wind with height. So that's what's taking place within our supercell storms. It allows the storm to rotate, which is the most efficient way by which we can transport moisture and energy upward within the atmosphere. Now we see lots of different types of storms, but our focus here today will be on the supercell, as you see in the lower left, and the squall line on the lower right. So in this first example here, you can see the radar on the bottom here, and we've got this line of storms that's running from the Ohio River all the way down to the Gulf Coast. And you'll notice too, in looking very closely, there's a line of red echoes near the lead edge. That is typical of squall lines, that your most intense precipitation, typically your strongest wind, is occurring right at the outset of that squall line. Looking closely at that, you'll also see some segments of this line that are accelerated out ahead of the rest, that are taking on what we call a bow-shaped configuration. Those are zones of enhanced likelihood for either straight line wind damage and or tornadoes, and we'll talk about that in a few slides. If we were to take a slice, just cut through this line and take a look at it from the side and take a vertical view of what we're looking at within that line, that's what the top picture represents. So on the far left-hand side, that's the atmosphere's wind profile. So we have a low-level easterly wind and the winds are out of the west and increasingly strong in higher and higher altitudes. So as this line is marching eastbound, it's encountering this warm and humid air out in front of it. It's forcing that air to lift upward. And the reason for that is you've got this rain-cooled, downdrafting, outflowing wind that's acting like a miniature cold front, that mechanical lift that's forcing the warm and humid air to rise. As air rises, it cools, it reaches saturation and forms into a cloud. This cloud that we see at the lead edge of the squall line we call the shelf cloud, and we call it that because it looks a lot like a shelf on a wall. The wall, in this case, being this heavy rainfall that typically follows right after the passage of that shelf cloud. So new storm formation as it's marching from west to east. Here's the updraft forming. Here's the downdraft that's tying into the environmental winds, which is actually then capturing stronger wind aloft and bringing it into the storm's downdraft and carrying it down towards the ground. These are different examples of shelf clouds, and they're all formed by the same mechanism, this downdrafting and outflowing of rain-cooled air at the base of the thunderstorm cloud. And again, what's taking place is this wedge of rain-cooled air is forcing the air out ahead of it to rise. So in the case on the right-hand side, these finger-like features that you see along the lead edge of the shelf cloud is literally the air being forced to rise, cooling, reaching condensation, but again in formation of these finger-like structures, which at times is misinterpreted as a funnel cloud. Now here's where we kind of combine radar and sky operations together. So we're looking at a squall line marching southeast across central Indiana. Here's the location of our radar. These storms are inbound towards us, and that's the reason why we're measuring in the velocities in shades of green for the inbound. So again, you see this worst is first, the strongest echoes at the lead edge, and lighter precipitation back behind it. In this scenario here, these pictures that you see, they're out of Thorntown and out of Tipton, were both pictures that were tied to this very event that occurred. The one of significance I want to point out is the Tipton picture on the bottom, because as you look at this, what's taking place here, Tipton is located right here. So they are still in front of that shelf cloud. And this line that you see right here represents the wind shift line, or the location of the shelf cloud in the sky. So at this moment in time, that shelf cloud is still off to the northwest of Tipton, and that's exactly what they're observing at this moment in time. So here's the lead edge of the shelf cloud right here, and here's the heavy rain that's just a few miles displaced behind the rear edge of that shelf cloud. Now, this is I-65 right here, this thin red line here, and right here is the location of Lebanon, right underneath the H in Thorntown. Folks at that location at this moment in time could literally walk out their door, look in the sky, and they would see a shelf cloud structure probably similar to what's here in Thorntown. This picture in Thorntown was actually taken before the radar image, because the radar image already shows the lead edge of the shelf cloud having moved down through there. They're already experiencing the heavy rainfall in Thorntown, and that's not the case in the picture there. Now here's another example of the same scenario happening. This was down in the Columbus area last summertime. And so here, as we look at this is the underside of that shelf cloud that is moving through this location. This is the leading edge, and it's marching from west to east, right to left in this case here. And this is the brighter sky out in front of that shelf cloud. A lot of turbulent look to the underside of that. This is that same storm and that same shelf cloud as viewed from somebody out of their car on I-65 heading down towards the Columbus area here. On this given day, we are under a slight risk for severe weather, and you can see by the blue dots there were reports of wind damage that came with this. But what's really of interest in this scenario here is the radar and what's taking place here. So you can see the location of where the heavy rain is at on the radar. This dark red line here represents the location of I-65. So you can see at this moment in time, the heavy precipitation is still some miles to the west of I-65. But as we turn to the velocity data, we see quite a different story. So as we move to the velocity, you can see here, now this is red and outbound away from our radar that's located up here. The lead edge of the shelf cloud is right along this arcing band of red echoes right here. So as you can see here, this leading edge of the shelf cloud in the sky is overtaking I-65 at that moment, while at the same time the precipitation is some miles behind. So there's another variation with regard to your shelf cloud wind shift as opposed to when the rain actually arrives. A lot like what took place at the fairgrounds when we had the wind shift come some 10 minutes before the rain came to the fairgrounds and brought down the structure. It was the wind that brought that down long beforehand. So here's an example of that taking place here. So these downbursts, as you can see here, are a strong downward and outward rush of winds at the base of the thunderstorm. When they occur on a smaller scale, we call them a microburst, and over a larger scale, we call them a macroburst. Now in this image here, we've got some interesting stuff that's taking place here. We've got a couple of cells out there, but of features to note on the reflectivity, note these thin blue lines that you see right here, and here's another one right here, and there's several others that are located down here, but these arcing ones represent the shelf cloud or outflowing of winds from these thunderstorms. It's a lot like throwing a rock into a pond, and what happens, you see those waves, they spread outward away from where the rock hit the water, and the same thing is happening here in the atmosphere, the outward spreading of the wind from the original location of the storm. So these couple storms here put out this boundary that you see right here. This picture that you see on the left-hand side and this shelf cloud structure that you see right here was being observed at this location here. So this person was looking out to the west and saw that cloud boundary there. Now when these squall lines take on this bowing configuration like we see here, again that's because the acceleration of the winds at a portion of that line causing it to bow outward, again as in the shape of a bow and arrow. So here is our bow-shaped configuration right here. We tend to find the strongest of the winds occurring in these things are at what we call the apex of the bow, or in other words, the location you place your arrow on the bow. That's where your winds will be at your strongest. Now, simply looking at the radar data, you can see exactly where that's at. You look for the strongest winds. And so in this scenario here, this is from the Lincoln, Illinois radar. Central Illinois, here's the state line. These storms are just about to cross into Indiana. But notice our sampling of the radar data here. We're looking at 80 to 90 knots of winds, which translates close to 100 miles an hour. A 100-mile-an-hour wind is a strong wind. But again, keep in mind, this radar's beam has been gaining altitude with distance. We're sampling about 7,000 feet above the ground here. So once again, we know we've got a 100-mile-an-hour wind, but it's at 7,000 feet. And the question always is it making it down to the ground, or at least a good chunk of that, and causing damage? And again, that's where you, the storm spotter, will come into play. Observationally, what we see take place in the majority of cases where a bowing echo has developed, if not the full force of that wind, a large portion of that wind does end up reaching down to the ground. So anywhere between, say, 60 miles an hour to 100 miles an hour of that wind will likely have reached the ground and will likely have caused damage in this case here. Notice along the upper end we have what is called this bookend vortex with an inflow notch that helps to create this rotation feature at the north end of this bow. That's an area where now you have counterclockwise circulation, so that's an area that you have to be concerned about the possibility of tornadoes. In a very strongly sheared environment, and we're talking again very strong winds aloft, maybe 7,500 miles an hour relative to surface winds at about 25 to 30. In such scenarios, then anywhere from the bow echo apex up to the bookend vortex is a zone where you may have small, brief tornadoes form. When these bow echoes become long-lived, marching across several states, causing damage across several states over multiple hours of time, we then refer to those as a derecho. And on this particular day, June 30th, 2014, there were actually 2 derechos that formed out in Iowa and Missouri and marched across northern Illinois and northern Indiana. And this is one that started out in the afternoon hours and marched into Indiana by early evening. And then the second one formed in the mid-evening hours and came into Indiana during the overnight hours. Of significance in that is this first one here actually was dissipating as it was moving into northern Indiana, but what was of importance with regard to that is it laid down a boundary, much like a frontal boundary. And that frontal boundary served as a mechanism for tornadoes to develop on. And so as you look at the reports here, when these things first started forming out in Iowa and Missouri, you see a lot of green dots, which represent hail reports that came out of that. But as you got further east and as this bowing structure became more bow-like in character, you see it starting to bow out here in eastern Iowa. Notice how all of a sudden the wind reports start to pick up. And then you get over into northeast Illinois and northwest Indiana where that boundary laid down. Notice now how you have a significant increase in tornado reports. So those are features that we have to watch for when we have such events take place. Here was one of those events that occurred back in November 2013. On this particular day, we had an extremely strong shear, Not so much instability, but we had a lot of shear in the atmosphere. And it's these high shear days that can bring about the likelihood of these small, brief tornadoes forming within the Boeco squall lines. We always tie this back to the environmental conditions supportive of severe weather developing. On those days in which the instability is not that high, the shear is not that great, but they're sufficient for severe storms. Storm Prediction Center puts out, in conjunction with the local offices, a severe thunderstorm watch. A line of storms form. A Boeco begins to form within that line. You get some wind damage out of it. You might get 1 or 2 tornado reports that come from that. Now you change that environment where you really ramp up the strength of the wind aloft. Now you're probably in a condition where the Storm Prediction Center, instead of having a slight risk out, they may have a moderate or even high risk out because of that extreme wind shear. Because then you tap into that wind, bring it down to the ground, you're going to cause lots of damage and lots of tornadoes. That's exactly what happened on this day here. So moderate or high risk days in which we're expecting Boeco squall lines, they're followed up by tornado watches, and Boecos forming those are the days we got to watch out for. On this particular day, in this map here, this is our area of responsibility here, but you can see some 16 tornadoes formed just within our area alone. Across the state, we saw 31 tornadoes on this day. That was the second highest count of tornadoes on a single day in our state's history. That's a lot of tornadoes. And when our annual average is 20. In low years it might be 10, in high years it might be 50 or 60, but on this day alone we had 30 because of the extreme wind shear. So these are the things that you want to be keeping in mind, that potential is there. Visibly, what's going to be taking place is what you see here on radar. Each one of these arrows here is pointing to what we refer to as a rotation couplet. That's one of these small rotation features that develop along that line because of the extreme shearing of the wind. A very strong push of the wind at one location will set up little swirls. You see that with leaves all the time in the wintertime. When it's a gusty day, these leaves get caught up in little swirls. Well, we see the atmosphere acting in the same manner here. Most of these tornadoes tend to be on the weaker side, EF0 to EF1, maybe 2. In this one here, we had one instance of a 3, but that's usually not the norm. In this next picture here, we take a look at that same line a little bit closer up. It's now moved farther east into the Kokomo area. And right here to the southwest of Kokomo, down in this portion where it's bowing out here, as we take a close look at the velocity data, you can see this well-defined outbound, inbound, or counterclockwise circulation that produced this tornado damage that you see up top there. And if you take a look at the exact location of where that circulation center is at, it's right here, right in the heart of that red echo, or right in the heart of the very heaviest of rain. And that's the unfortunate problem we oftentimes see with these Boeco squall lines, is they get embedded within this heavy rain and they make it very hard for the storm spotters to see. In fact, very dangerous for those storm spotters to be in such a position. Here is our survey from that given day. So there was the track of that particular storm there, starting back out to the southwest and tracking right on through Kokomo there, and you can see the various EF0 to EF1, EF2 damage levels here. Let's see if we can't zoom into one of these here, take a closer look. Let's take a look at this damage here. So here's an example of some of that EF2 damage, and by EF2 what we're looking at here is, as you see here, that a lot of the roof structure is gone. One of the exterior walls has been knocked down by the force of the wind. So there you have an example of some EF2 damage that resulted in that particular area. Let's take a look at one of the other ones that was reported there. Take a look at this one here. Now in this one here, the storyline is a little bit different. Here you see what appears to be a more substantially damaged home, but this was actually a building that was under construction at that moment in time. And the wind was such with the home under partial construction that it was able to take down a lot more of the home that you would normally not see during a typical EF2 damage scenario here. But again, this is an example of some of the surveying that we do when we're out in the field, and again, what Tom Harbin oftentimes helped us with when we didn't have a chance to get out to parts of Madison County. So again, this issue that we run into of rain-wrapped tornadoes, good, this one's running here. So this is an example of what these can look like. So you can see here this tornado ripping across this parking lot here. And the extreme updraft that is tied with that tight vortex, this tremendous pressure drop, lifting these cars and tossing them like toys, despite the fact this is probably not more than 50 foot across, Probably didn't last more than but a couple of minutes, but it is embedded in rainfall. But given its short duration, small size, if you're not at the right spot, you're probably not going to see it. You'll see the aftermath. From our perspective, it might be a small enough circulation, it might not even be visible on radar, or it might be short enough duration that it might literally have formed and died in between the time frames of our radar sampling in that given area. So these small, brief squall line tornadoes can be a real issue for us. But what we watch for with squall lines is that shelf cloud, this low-hanging cloud running parallel to the ground with a smooth bluish-gray sky behind it. That's the heavy rain that usually will follow right after its passages. Again, straight line wind is our main concern, but we also know that these can be hail producers. These can, as you saw by example there just in the last couple slides, these can be tornado producers. So we want to keep an eye out on that as well. So supercells, kind of like the Superman of thunderstorms. And what distinguishes these storms from the squall lines that we've just observed in some of the ordinary everyday thunder showers is the fact that these storms develop a rotating updraft. They're a storm in rotation. They are literally become a miniature low pressure system, thus the reason why we call these a mesocyclone. We're looking at the south side of this, viewing a storm off to our north. Huge cloud in the sky. Here's the main updraft right here. Storm typically will level off at some point in the altitude, up at the higher altitudes of the atmosphere because it becomes stable above that. So that kind of serves as a cap on the atmosphere. And that cap maybe 30,000 feet in the atmosphere in a cool season, and it might be 60,000 feet in the heart of the summertime. But some leveling off point where we form this anvil that's stretched downstream by the upper level jet stream winds. But in the cases where updrafts are very strong, we develop overshooting tops because that air has so much momentum it can't stop at its normal stopping point. It's like taking a car moving at 80 miles an hour and expecting it to stop in 20 feet. It's simply not going to do it. It has too much momentum. You can see on the rear side of that storm tower, flanking lines and dew cells beginning to develop that will become part of the main storm tower themselves over the course of time. The key cloud feature we're watching for here, however, is the wall cloud. That's this cloud feature you see that right down here. So we've talked shelf and we talk wall. That's the two main clouds we're concerned about here tonight. Shelf clouds with straight line winds associated with downdraft and outflow. Wall clouds tied to cylindrical and upward motion, rotation, and tied to the tornadic development. What's key in identifying these is first of all their location within the storm, and second of all where they are at relative to the rest of the cloud base. So here you see your main cloud base, this line right here. And notice how your wall cloud is well below. That cloud formation is well below the rest of the main cloud base. The wall cloud is a representation of where the updraft is starting at ground level. So air is rising upward here in a spiral-like fashion, going to increasing altitudes, tilting forward with height because of the increasingly strong wind aloft. Descending from that wall cloud, we would see the development of your funnel and or tornado. Now, not all supercells are tornado producers. In fact, only about 1 in 5 end up producing a tornado. But what distinguishes what we see in supercells from squall lines, it's a completely different story. From a hail perspective, the squall lines, again, may be upwards of an inch diameter hail that may come out of those, maybe a little bit larger. Generally more in the case of pea to marble size hail. In the case of supercells, they'll run the range from pea size on the low end to softball size on the high end. So in other words, the big hailstorms that are coming from storms are coming from these supercells. Regarding tornadoes, your squall lines, generally EF0, EF1, winds for the most part under 100 miles an hour. In the case of supercells, these run the range from the EF0 low-end tornadoes to the EF5s that destroy the homes in their path and throw them hundreds of yards away from their original location. So again, it's the supercells that cause the violent tornadoes and the violent damage that ties with those. Straight line winds out of either the squall line or supercells, they both can be one and the same. They might only be producing 20 to 30 mile an hour wind downdrafts and outflows, or either one of them can be producing a downdraft and outflow in excess of 100 miles an hour. And again, that's where you turn to your radar data to get an idea of what's going on. So as we look at radar data, here is the look of the supercell on radar. Broad, forward portion, and that narrows to a tail that has a hook. So the TV meteorologists, when they refer to a hook on radar, this is what they're referring to. It looks like the shape of a hook, and that hooking is a result of the counterclockwise circulation that has wrapped the rain around the back and the south side of that circulation feature. Where's that occurring as you're looking at the storm in the sky? Note the position of where the tornado is at. It's back on the rear side, underneath the updraft. That's that yellow curly cue that represents the rotating updraft that is forming that storm. That's where your wall cloud formation is going to be. That's where your tornado will be coming from. From the radar perspective, it's going to be coming out of this portion of the hook located right here. Notice we got a couple of downdrafts going on. We got that light blue arrow in the forward part, and again, what took place there? Updraft is creating precipitation, both rain droplets and hail. That updraft is tilting forward with height because of the strong wind aloft. That rain and hail begins to fall down to the ground because of the weight that it has. It just simply can't be held aloft by that updraft any longer. Comes down to the ground. The wind reaches to the ground, spreads forward and rearward. That which spreads forward forms a shelf cloud along the lead edge of that storm. This is what is referred to as the forward flank of the storm, and this is the forward flank downdraft in that storm. And again, that air is spreading both forward and rearward towards the updraft, and some of it actually gets ingested into the updraft. Notice we also have this zone of hail right here in front of the wall cloud and tornado. That's generally where you're going to see your golf ball and larger size hail. From the radar perspective, you'll see that largest of hail fall from one of two areas. One, anywhere where you're seeing the shades of pink, purple, or white from our radar perspective, or you're going to see it fall from the southern edge of the red echoes out in front of the hook echo. And why is that the zone for the largest hail? Well, it's pretty simple. It's the same thing if you, say, for example, trying to throw a tennis ball versus you trying to throw a shot put. Which one are you going to throw farther? The tennis ball. It's a lot lighter. Shot put, you're not going to get it very far. The baseball and softball size hailstones, they're not going to move away from their lifting source, the updraft, before their weight will cause them to fall close to the updraft source. So again, miniature low pressure system. Your green circle on the left, black circle on the right, draw a big L there to indicate low pressure center. Counterclockwise rotation center at that location. And extending outward from there are boundaries. This boundary right here is a cloud edge that's separating the warm and humid air that's feeding into the storm from the rain-cooled downdrafting air in the forward flank downdraft. Over here in the lead edge, forward flank downdraft, shelf cloud formed at the lead edge acting like a miniature cold front. That's what this boundary here is representing. And then back here, this is also an additional cold front. That red downward arrow, the rear flank downdraft, is cooler air from aloft being brought down, creating a shelf cloud, acting once again like a cold frontal structure. Positioning for storm spotters is one generally here somewhere in the inflow air. You've got a great vantage point to the wall cloud and tornado from here. Perhaps a position back here behind it where again you're outside of the rain. You've got a great view into the wall cloud and tornadic portion of the storm. Positions elsewhere to the east or to the north, not very good ones because you're not likely to see through all this heavy rainfall to that part of the storm that produces the tornado. Now here we have kind of, again, this combination of looking at the sky and looking at the radar and seeing what's going on. In this particular case here, this was out in northern Illinois near Rockford. The Storm Prediction Center put out this MCD, mesoscale convective discussion, and this area that's hatched in red here is a representation that they thought this is an area that's going to need a tornado watch here shortly. The reason for that, low pressure centered over Iowa and Missouri. There's a strong cold front position trailing southwest out of that, but also more important is there's a warm frontal boundary up here. If you'll notice where my hand is at here, these features that you see right here are the surface observations, and they're pointing in this direction here, which indicates the direction of the wind flow or winds out of the south. Along my hand here, you'll notice the direction of those up there. Those are showing winds out of the east or southeast. So you have a substantial change in wind direction. That's the location of the warm frontal boundary. That's that mechanical lift zone that can act on that unstable air, and that's where this particular storm formed. So with that, here's our hook echo. Here's our forward flank downdraft. Here's the hook. As we take a look at the velocity data, the radar in this case is located to the right-hand side here. So with green is inbound this way, red is outbound that way. So right here at the intersection of the two, you have your mesocyclone or low pressure center, counterclockwise circulation. That feature there, if you tie it in with the road, you can see it is tied in right here with that black circle area. The picture that you see down here, this was the position of the people that took that picture. They're located right there on the interstate looking due north at that feature on radar and that feature in the sky. And so you have your mesocyclone center. That's where your wall cloud structure will be. That's what you have here, and actually probably even part of this back here too, but most concentrated, that part right here is our area of focus. And why is that? Well, you can see you've got a tornado in progress right at this moment in time. So you've got the condensation funnel as well as debris being lifted from the ground. Other features of note in here, however, remember as I mentioned before how that velocity data can help you identify where wind shift lines are at? Well, right here you have a boundary here. Green inbound, red outbound identifies where a wind shift line is at. That line right there represents the location of the rear flank downdraft shelf cloud, and it's wrapping right into the mesocyclone. Visibly in the sky, here is that rear flank downdraft cloud edge right here, and it's wrapping into the forward side of your rotating wall cloud. So again, tying what you see in the sky to what we see in the radar back into the idealized model that you see in the bottom left there. Now here again is another case where we're tying sky and radar together. So as you see that video start up there, you can see the cylindrically lowering of the cloud base that's rotating upward. So you've got a rotating wall cloud in progress right over here. That video that's being shot there was shot from this position right here at the center of this X. So these videographers were standing to the east of this tail portion of this supercell. So here's your forward flank downdraft that's over and beyond the radar. Here's the hook echo portion back down here. This little yellow circle that you see right there is the radar software saying there should be a mesocyclone there, meaning there should be a wall cloud there. And it may or may not be in rotation. In fact, this purple triangle is the radar saying there's a really strong rotation there. There could be a tornado. And there may very well be, because we saw a little bit of debris being lifted there. So here what you have, storm spotters standing here, they're in the rain-free area, they're looking due west at this hook echo that has a rotating wall cloud. Great, good information to pass along to the Weather Service. Now, when you put this radar into looping mode, that gives you an idea of the direction the storm is moving, because it's really important for those storm spotters. Radar in looping mode, this is the broad white arrow here, this storm is tracking to the east-northeast. And so what that means for the spotters, this mesocyclone that's due west of them, is going to track to the east-northeast and eventually end up to a position just north of where they are located. So as long as the storm behaves as it has been before, what they're going to see here is it looks like it's going to be coming out of the screen, which means going eastbound, but it's also got a component towards the right, meaning it's going northbound as it's coming eastbound. And so it's going to pass just to the north of them. But having said that, we always caution spotters to make sure that they have north-south, east-west access away from that location in case the storm were to decide to take a turn towards the right, towards the more unstable air that's feeding that, because at times that can happen. And in such scenarios, when you see that happen, you want to get in your vehicle and you want to get southbound out of the path of that storm, as you see here. November 2013 in the Lebanon area. Here is our wall cloud structure. Here is rear flank downdraft structure right here. Here's that clear slot forming behind the tornado. There you can see the hook, although it's not a real strong hook and not a real strong rotation, but nevertheless it was an EF0 producing tornado. Let's take a quick look at the path of this while we're here. So again, this was one of the 31 tornadoes that occurred on this given day. And there's the path of that. You can see it started southwest of Lebanon and moved right into the southwest edge of town, went through this factory area here. Let's take a look at this EF2 damage here to show you an example of what the EF2 damage was. And you can see in this particular case here that there is a lot of shingle damage, and that one that one wall was blown out by the tornado's force there. The Henryville tornado, which again was exhibiting these same characteristics. Your well-defined hook echo with a debris ball on its tail, the pink and white shades here representing the baseball and softball size hail that was falling from this storm. The very intense counterclockwise rotation that was present in this EF4 tornado. And visibly within the sky, this is I-65 northbound, a couple miles south of Henryville. You can see the well-defined wall cloud structure here. Here's your rear flank downdraft shelf cloud that's wrapping to the forward side of your wall cloud structure. This vertical column here is the tornado that's crossing the road, and here's a little bit of rain behind it, but here's that brightened or clear slot that has helped form right behind that. So again, this is a feature that often is kind of like that 1, 2, 3 step process before the tornado forms. We see it again here in this slide. Rear flank downdraft shelf cloud that's wrapping around the wall cloud structure, and here you've got a funnel that's halfway to the ground. This will likely end up becoming a tornado. We see that all culminate into this single video here that was shot back in 2004 but remains a perfect illustration of what took place. Rotating wall cloud with a funnel beginning to form. This was southwest of Lebanon near Jamestown. The rear flank downdraft starting to get its act together. It's starting to clear out the sky here. What remains is the rear edge of the wall cloud, the base of the wall cloud, and the funnel beginning to descend further to the ground. So again, this 1, 2, 3 step process prior to tornado formation. And about right here, you now start to see debris lifting from the ground, so it's now a tornado. Even though your condensation funnel is not in contact with the ground, you're lifting debris, you're causing damage, you've got a tornado. So again, that's the process that we see take place visibly within the sky as these are forming. Again, we can watch that evolution through the intensification of the rotation, not only through the depth of the atmosphere, but over the course of time and the brightening of the colors and the compaction of that rotation mesocyclone couplet. Speaking of significant tornadoes, this was the Washington, Illinois. That's near Peoria, the Illinois River there in central Illinois. So you can see the strong rotation on the right, the very well-defined hook echo on the left with the debris ball signature there. And this was safety cameras inside this folks' home, a couple of them on the front driveway, one out the back door, and one on the inside of the house as this tornado came down their street. And you can see all the debris that's flying around in the neighborhood here. In just a moment here, you'll see a limb go down on that tree. And in just a moment here, things are going to go crazy. Right there, so everything flying, in fact, inside the house. So windows probably got breached, roof probably got torn off, and again, you can see the outcome of that is all that debris flying around. But this was the end result of that tornado. Again, an EF4. And EF4s and EF5s are violent tornadoes that leave nothing much above ground but complete destruction. And that was the path of that storm from that area up into Chicago on that given day. I want to caution you to lookalikes because there's features in the sky that look a lot like a funnel and or tornado, but what you're always watching for is the evidence of distinct rotation about a vertical axis, rapid upward motion within those distinct axes. That's what you're going to see in both the funnel and or tornado. The 3 of the 4 of these examples that I have here are simply cases in which you have fingers formed on a shelf cloud. This one here is a rain shaft that's coming out of the base of that particular storm cloud. This one here is a fire down in Louisville that looked a lot like a tornado coming out of the base of a dark cloud. This one here out of the Trafalgar area to the south of Indianapolis, you can see a well-developed shelf cloud here that's hanging relatively close to the ground. Maybe that part of that is the horizontal view issue that's taking place here. But when you take a look at what's going on radar, this is the position where that picture was taken from as they were looking off towards their northwest. You can see the precipitation is well off to the northwest. Really no evidence of a hooking-like structure. Really no solid evidence of a distinct rotation tied with anything in the way of a hook-related feature. So this is, again, just one of these look-alike features. But nevertheless, it certainly is a feature of concern. It's hanging down close to the ground. You want to take a close look at it. Look for the evidence of rotation. Look for the evidence of flying debris. If those things are taking place, then it might very well have been a tornado. But in this case, that's not what was occurring. Same story here. Looks perhaps like a funnel, perhaps like a tornado, but that same feature from a different view. Again, it's those fingers along the lead edge of the shelf cloud. So you want to be cautious with regard to what you're observing and what you're reporting. Now, we rate tornadoes based on the amount of damage that they cause, and those ratings go from an EF0 on the low end to an EF5 on the high end. We categorize tornadoes as weak, being EF0 and EF1 tornado character. Wind speeds, for the most part, below 100 miles an hour. They account for about 85% of all tornadoes. Only 5% of all tornado fatalities. They're on the ground for just a short period of time, maybe a few miles at most, probably not more than 50 yards wide in general. But because the winds aren't that strong, they're not on the ground very long, they're not very wide, and they don't have a lot of wind to blow a lot of stuff around, again, they don't normally cause a lot of loss of life. The stronger tornadoes, the EF2s through 5s, winds well over 200 miles an hour when you get into the high end. You can see by the numbers there, they account for the remaining 14% of tornadoes, but 95% of the fatalities. These tend to be larger and longer lived, and with the stronger winds and bigger size, they're throwing a lot more stuff around, increase the likelihood that people are going to be hit by flying debris and die. If we further subdivide this down to just the violent tornadoes, the EF4s and 5s, which destroy homes, those only account for 2% of all tornadoes, 70% of all tornado fatalities. So by far the majority of people who are killed within tornadoes are killed within the rarest of tornadoes. The Henryville, which killed a dozen, was an EF4. The Washington, Illinois was an EF4, and I think they killed several people were killed in that one too, I think. I don't remember the numbers offhand. So we're fortunate that not more of those occur. So from a storm spotter perspective, it's all about being aware of your environment, knowing what's taking place out there, knowing what the forecast is called for, and whether or not there's a watch box, and whether there's warnings been issued, and whether there's been reports from other storm spotters. So when that storm gets to your neck of the woods, you got an idea of what to anticipate. Once that storm does arrive, you want to make sure that you're not in harm's way. Now, in the case of a squall line that's lined up from Lake Michigan down to the Ohio River, you're not going to get out of the path of that. But if you're in your vehicle, at least you can orient it into the direction of the wind to minimize its impact and the potential of tipping your car over. And if you're at home, you can get inside shelter. But again, it's all about trying to place yourself in the right place with respect to the storm to keep yourself out of harm's way as best you can. With regard to reporting, that pamphlet that you grabbed out at the front door has a listing of all these as well as the ways in which you can report. But as you can see here, the list is long. We need to know what that storm is doing because, again, we see what's on radar, which is up in the sky. We're only guessing at what's taking place down on the ground, and we're pretty good at guessing because we've seen this many times over. But each storm is different. Each storm provides different damage and different data, and we need to hear from you with regard to that. With regard to how to report, there's a lot of different ways. These are all referenced on the handout again. Our webmaster email site is a good place you can send us pictures to. Like us on our Facebook page and then send pictures through that route. If you've got a Twitter account, you can use hashtag INWeather or NWSIND as methods by which you can report information into us. You can use our website. There's a submit report form on there. You can report through that manner. The old-fashioned phone still works. And our amateur radio operators, and there's a lot of those here in this county, you still remain our number one source of weather information and our number one source of reports for us. So we greatly appreciate your efforts you've provided. This represents the 39 counties that we serve across Indiana, from Lafayette in the northwest to Muncie and Winchester in the northeast to North Vernon and Seymour in the southeast and down to Vincennes in the southwest. And each one of those counties has an amateur radio club or an amateur radio operation of some sort. And so when watch boxes get issued, these clubs and or amateur radio operators get themselves organized. They start to report into a net control who passes information into our amateur radio operators that are at our office. And again, pass that information along to us and help us with that determination of the needs for warnings. That submit report form, this is our front page, weather.gov/IND, and this first tab on the left-hand side that says current hazards. The drop-down menu has a selection for submit storm report. You click on that and a report form pops up with the current date and time already populated. You simply fill in your county, your location, and by location, if you want to do lat-long coordinates, that works for us. If you want to fill in I'm at 8th and Main in Anderson, that works for us. If I'm at County Road 300 East and 400 South out in the outskirts of the county, that works for us as well. But just give us some kind of bearings that we can work with, a time frame in which this has happened, and pick and choose the elements that you've observed there. Submit the report, it sends it into our office, we kicks off an audible alarm on the PC, and during active weather we know here comes a report from a storm spotter and allows us to check that. So there's multiple ways by which we're monitoring what's going on out there. Again, we're through those reports coming into our computer, the phone calls, the amateur radio reports. We're also monitoring Facebook and Twitter accounts. And so pictures that are sent are great. That provides that visual for our meteorologists so they can apply that visual to their conceptual model in their mind of what this storm should be doing based on what they see on radar. And it helps them in that warning process. So here's a couple examples in which that occurred up in the Lafayette area last summertime. Here are some additional ones, a picture of a funnel cloud here, a couple of shelf cloud pictures on the bottom here, even words, hail and Waldron, pea-size, a few larger. That's important information to us as well. We would not have known that otherwise. So every little bit of information helps us have an understanding of what that storm looks like, and so we can use that for comparative purposes for strengthening or weakening or new cells forming. all that kind of ties together because it gives an idea of what the environment is capable of on that given day. Our website is one source. Our one-stop shop weather story down here to the bottom left. Our radar thumbnail here in the bottom center. Any kind of product that we've issued are listed over here to the right-hand side of the map. That hazardous weather outlook, that 7-day forecast we have for the potential for severe weather. If we're expecting significant weather taking place, we'll carry a story up here in the news headlines. It'll be a PowerPoint 3 or 4 or 5 slides long talking about the impacts, timing, and so forth with regard to what we anticipate happening. So that's our website. Here's our hazardous weather outlook breaking into the first 24 hours, days 2 through 7, and then a statement at the bottom as to whether or not you as a storm spotter might be able to help us out in the coming day or so. If you really like to get into it, again, I talked about the Storm Prediction Center earlier. This is their website, spc.noaa.gov. This is their front page here. Mousing over any one of these tabs here, you can take a look at their outlooks, current watches in effect, any kind of mesoscale discussions that they might have, storm reports, the mesoanalysis. That's the one I showed you before, and I'm going to show you here again in just a moment. They provide details about the atmosphere at that moment in time. But again, this idea and this concept of being safe from the storms, it's about getting in, getting down, and covering up. It's kind of like the fireman stop, drop, and roll. Getting into an interior area on the lowest floor available to you, covering your head with your hands. That's the key actions that you want to do. But it all ties back to being aware that something's going on out there. If you're simply watching TV, you have no idea what's going on outside, maybe it's satellite TV, you're not watching local stations, well, at least one saving grace with regard to that is the recent technology of the wireless emergency alert that is embedded in all smartphones. It's not an app that you have to load in here. It's there in your phone automatically. So if you're under a tornado warned area or under a flash flood warning and you're in that area, this phone will alert you to that. It has a unique vibration and also unique audio, neither of which you've maybe heard before until you see it and hear it for the first time. But it alerts you to the fact, what's going on with my phone here? So you pick it up and you look at, oh my gosh, tornado warning for my area. Time to be taking cover. All thunderstorms produce lightning. It's our nation's #2 weather killer. Maybe it's #1 right now. I don't know. It kind of goes back and forth between flood and lightning as to which one's doing it. I think actually our lightning numbers have been dropping because of the lightning safety campaign that we've had for the past decade or so. But inside a building like this that has plumbing or wiring that can carry that electrical charge to the ground for the lightning is a safe place to be. Inside your vehicle, that metal shell that surrounds you is your protection. So as long as you're not in contact with outside sources, you're protected from that lightning. But pretty much anywhere else outside is not a good place to be during a lightning storm. And when storms occur, they all bring heavy rainfall that can lead to flash flooding. And so you don't want to do what you're observing here in this video. You don't want to be driving through water that's flowing over the road because you can't tell the depth of that water. You cannot tell the condition of the road surface underneath that. You might have driven that road 100 times before that had a little bit of water on it, and it's that 101st time where it's just deep enough that it can wash you off the roadway. Here's a case. Gosh, you can see that half the road is washed away. Why would you want to drive over that? In a hurry to get home. And a lot of times, a hurry to get home, you become a statistic for the National Weather Service. So don't mess with water. Hopefully you've seen through these many examples how your sky and your radar work together, how you utilize your velocity data to identify your wind shift line or where your shelf cloud is at, to identify your rotations and watch those over time to see whether they're strengthening or weakening. How those tie in with the updrafts and downdrafts. The downdrafts tie this to the circularly shaped wall cloud, which in rotation may lead to a funnel or a tornado. And your shelf cloud, the elongated cloud structure, again, those tied back with the radar signatures. Use those two pieces of information together. And we've talked reporting, so that's all we have here for today. But before we head out, anybody might have any questions with regard to what's been covered or maybe what's not been covered? Yes, Tom. That's a very good point. Even though rain-wrapped tornadoes are occurring, there is still a loud sound associated with either the roaring of the train, the jet aircraft. There is a distinct sound to the atmosphere when a tornado is approaching. So at least if you can hear well, you can at least observe that aspect, that you use one of your senses to observe what's taking place there. Good point, Tom. All right, well, I guess we're all wore out. I know I am. Well, Tom, again, thanks for the many years of service to this area here. It's been a pleasure working with you over the years. Again, like I said, you truly are the best at it here in the public official business. I always trusted everything that you did for us and appreciate that. And to all you spotters out here, I appreciate your help as well, because you never know what that report that you provide might be the one that's the impetus for the warning that we issue that saves lives someplace. And it's an important role that you play, an important role we play, but as long as we're playing together, that's all about developing a weather-ready nation. So thanks to the Madison County Emergency Management, thanks to the folks here at the casino here. We greatly appreciate the use of this facility here. It's a great facility. We hope to be back here again next year. So thanks for your time, folks. Enjoy the rest of what's left of the evening. Prepare for severe weather because we know it's coming. Thank you very much.